Whoa! You thought we were done? Not even close. What if we had something like this? Oh, no, scary. But what if we tried spinning it? Oh yes, this is the new method to find different revolutions now to get into a solid. This time though, we can actually make something round versus something polygonal as our last two times using triangles and squares. So this time we can get an axis and we can rotate about it, and then you can end up with a three-dimensional shape, which is evolved from the actual function itself as we go and integrate it across the two different limits, just like how we have been before. Oh yes, and so with something like this, as you can see, if we took any sort of differential in the x, so a little subsection of, let's say in our case, similar to a rectangle in a Riemann sum, but if we rotated it about the x-axis there, you can see that it makes a cylindrical shape that actually has a sort of volume, but instead of calling it a cylinder, the way they like to call it in calculus is a disk. Yes, indeed, that is how they're going to go about making these types of solids now that are from a revolution of a function going across either an axis or a specific line equation. And from there, we can then find out the actual volume that comes out of that kind of rotation, which of course will most likely be solved through an integral. So how then could we find the volume of these types of functions? Well, for one is that we are going to get a type of equation that we will need to memorize. But
now what shall we do?
Well, let's take it one step at a time. We have a disk now because it has been rotated into a circular motion. That means that the height of that function is denoted as r, the radius of that disk. And so thinking of this as we said before, a cylinder, if we thought of it as a simple cylinder, in that case, well, a cylinder's volume is very easy. For us, geometrically, it's just going to be the volume is going to be equal to pi r squared, so the area of the face of that circle of the cylinder, multiplied by the height, or in this case, the thickness of that disk. Now, in our case though, we use the word disk because we're trying to show that mathematically, the actual thickness of that cylinder is extraordinarily thin. So thin that if then we added up all of the disks that go about across all the different radii going across this function, and if we added all of them up, then we can get the full volume of the solid. Adding up all the heights of the function going across, oh, that sounds exactly like a definite integral. And yes, it is. So instead of thinking of any sort of initial height that these cylinders will come across, instead of calling it one set height, we are just going to add it all the way across from limits from A to B, of course, because this radius is not defined by a single number, but the radius is defined by all the different heights coming across from the limits that we are assessing this function. Oh yes. And so with that, instead of calling it a singular h, the actual volume from this rotation is going to then come from, instead of calling it singular h, we can take the integral and going from A to B and going all the way across all the different disks based off of the heights, again, which is now defined as a function. So in our case, the radius is going to be a function, pi r squared, in accordance or in terms of x for this type of function. So something to note, of course, is that we are using dx if the actual heights are in terms of y, because again, the function is in terms of x being the variable that goes across the actual function. But did you know that you can also go for, again, if this is going to be a vertical rotation, but did you know that we can go about it in a horizontal rotation? Oh yes. So what if instead we had ourselves a function that rotated about that way across the y-axis? Oh yes, So instead, if we had a function something like this, and then we had our radius going across that way, the horizontal sense, then we must change that integral over to a different set here. So same idea, we're still going from a to b for that volume. And of course, the pi r squared is going to stay exactly the same. It's just that instead, we're going to take this in terms of dy. Now, I know for a lot of students, this might seem kind of weird. Why in the world is dy going to be horizontal? I thought the y was supposed to be a vertical variable. Well, in terms of the way that we're doing this, again, we are integrating in terms of y. Again, that means the function is now having y climbing from a to b. Think of it that way, right? The limits in which we are integrating, that's the way in which the variable is going to climb. As you can see, the y variable is going from a to b, now listed as limits there from where the function hits the axis. Well, that's going to be rising from a all the way to b in terms of y. And back to our first example, it's dx for vertical rotation because our variable x here is going to be climbing across the two limits through the x values. So at least for that is an easy way to remember it. Whichever way works best, of course, is just that you need to know whether which is going to be used for vertical rotations, which one will be used for horizontal ones.
Wait.
So that must mean that we have a few other things that we need to go over. One, of course, is understanding what the r function will mostly look like. And of course, for ourselves, is actually running that definite integral to then find the actual volume. So let's go right about into a simple example problem. I think for this, the demand will be about a horizontal one so that we can see what that looks like. And it should come up right about here.
Whoa, it hurts!
Whoa. Oh man, we've got ourselves a real doozy of an example here. And so we are looking to find what this problem is stating for right here. Tell us to find the volume of the solid generated when the region bounded by y is equal to x squared, x is equal to 2, and y is equal to 0 is rotated about x is equal to 2. We've got a lot of stuff going on here, so let's see if we can identify that. First off, we're dealing with y is equal to x squared, as seen over here with that parabolic shape right there. And then the x is equal to 2, which is going to be that straight line right there at that value of x is equal to 2. And y is equal to 0, of course, which is just going to be the x-axis. But our rotation is going to be about x is equal to 2. So right there is where we'll be doing the rotation. And any sort of section there is going to be rotated about that horizontally. So remember, if we're rotating about x is equal to 2, usually what I like to do as well is draw that little swirl there on whichever axis of rotation we have, just so we can visualize which way we're going, which, as you can plainly see, is a horizontal rotation for this type of solid. Which then, of course, means that we need to bring up that equation of the volume being equal to pi. Given that's a constant, we can leave it to the outside. Pi multiplied by the integral going from a to b, this time of r squared, and in this case dy for a horizontal rotation. Okay, and because of that, then we can go and see that we are, in terms of how we are going across about this, again, we can't be going horizontally this way because we are rotating about a horizontal plane, meaning that we are traveling, again, as we see with the little rectangle there showing which section it is that we're going up by. Again, our limits are traveling vertically to match that. So because of that, we might be thinking that, oh, the limits must be going from 0 to 2. That would not be the case. Again, we are traveling vertically up to match those sections that need to be rotated about horizontally. And because of that, our actual limits are going to be going from, so if it's a to b, it's going to be going from 0 to 4. And 4 being the highest it is for the y value for that type of function. Again, a lot of mistakes might be happening for those that might want to be jumping the different parts of the problem to just hurry up and get this over with. Well, that wouldn't be the case here. Again, we can't be using x squared because we are integrating in terms of y. Again, that fact is already set for us. And so because of that, we actually need to change this back in terms of y instead. Again, we're using dy, we need to change functions back in terms of y. So the function y is equal to x squared is then going to be changed to the square root of y being equal to x. Again, we need things now as x as the output of the function and y is the input of the function because we are doing a horizontal rotation. But not only that, if you notice here is that the radius that we mentioned here, right, is actually the distance between that x is equal to 2 line all the way to where the function is, right? So because of that, we can't just be calling the square root of y as the actual radius, because square root of y is actually going to be the distance between the radius, not the radius, sorry, between the axis and to that function. That is not useful to us. What is useful to us is knowing that we have a distance of 2. Again, that's a solid distance of 2 because x is equal to 2. That's a distance of 2 straight from the axis all the way to that line. And so because of that, we then need to say that, okay, we have that full distance of 2, but then we need to take off that square root of y from it so that all that we're left with is that section that we want to use. Again, for a lot of students, visualizing this on the graph, again, showing where all these distances are coming from, usually is a very good way to kind of get the idea as to what needs to be integrated. So with that, we can then define our radius as not just 2 or not just as the square root of y, it's 2 subtracted by the square root of y. Again, we are going to need something like this in order to show what the radius looks like, again, just from the distance from the axis all the way to the actual function itself. All right, so it looks like we have everything we need to then plug it in straight to our function right there. So as we said, our limits of integration is going to 0 to 4 because we're going off of y values. And then we're going to take 2 minus the square root of y, all that squared dy. All right, so it looks like we have everything we need in order for us to plug in for this type of integral. And so we first will need to FOIL out the 2 minus square root of y all squared for us to then integrate across each independent term. So with that, we'll keep the same integral of pi on the outside multiplied by the integral from 0 to 4. And we just run a quick FOIL of a positive 4 minus 4 times the square root of y, and then adding a positive y to make sure we cancel out with the negative term, and then dy will still be there. So with that, we can then integrate across each term. We're still going to keep the pi on the outside, and then we will get a 4 times y subtracted by, this time, this is going to be y to the 3/2 power. And so because of that, we will then need a coefficient of 8 over 3 in order to cancel out with that, leaving the 4 on the outside after we bring down the exponent. And lastly, we have a y squared over 2. Okay, and this integral is still going to be evaluated from 0 to 4. Now, thankfully, because we do have the limit starting at 0 and with y's across each term, the second term just goes straight to 0, so not a problem for us. We just need to deal with that 4 coming out as a way to analyze that limit. So the pi is still going to stay outside, and then we just need to plug in 4's across. So it's going to be 4 multiplied by a 4, and then we're going to subtract it by 8 over 3 with a 4 raised to the 3/2 power. And then lastly, we're going to need a 4 squared over 2 as a result of that. Okay, so we can then run some algebra here. Again, that second term, if we want to show it, is all just 0 at the end, so it's not any of our concern. But we can then run the rest of all that straight through. And so let's have a look here. So the pi still is not yet to be checked out from the problem, but we have a whole 16. Now subtract this of 4 raised to the 3/2 power. That's going to be a whole 8. So that's going to be minus a 60. So it's 8 times 8, so 64 over 3 because of that. And then we're going to add, so the 16 now over 2 is going to be positive 8 as well. Okay, so because of that, we end up with a 24 over here, but then with the over 3 denominator, so first it'd be a whole 24, but then an over 3 would mean that it's a 72 over 3 because of that. So we can write that really quickly. So first that we can combine the like terms, so 72 over 3 minus a 64 over 3. will then give us a nice positive 8 over 3. So in the end, it's going to be 8 pi over 3 as the resulting volume for this type of solid. All right, so although the actual integration took a little bit of time because it just needed to be done so when we do it by hand, the main purpose of this type of problem is knowing how we can set up the radius, especially for something that is a horizontal type of revolution, right? So again, those are kind of the two main steps of understanding where you're rotating, so which kind of variable you're going to integrate by, and then understanding what the radius truly is. As one last iteration here, again, the radius was defined as a distance from the actual line of x is equal to 2, and then the distance straight to that function of the square root of y. So because of that, again, very similar to doing the top minus bottom that we've done before, it's going to be the longer side, so that 2, again, the distance from 2 down to that radius. So it's 2 minus the square root of y, which is what we came up with. We just follow that formula, and we ride our way home to finding this type of volume. So that is pretty good for now. We'll be coming back again tomorrow with another method known as the shell method, and that will include its own examples and formulas as well. So we'll take that for now, and we will see you again next time.